Imagine for a moment that you are a systems engineer at NASA, sitting in a dimly lit control room surrounded by flickering monitors and the quiet hum of high-powered servers. For years, you've been trained to expect the predictable. You know how stars are born, you know how galaxies rotate, and you definitely know how the Big Bang is supposed to have set the universe in motion. But suddenly, a notification pings on your screen. A signal has just arrived from the deepest, darkest corner of the observable universe. It has traveled 13 billion light-years through the cold vacuum of space, carrying information from a time when the first stars were barely beginning to flicker into existence. But as the data begins to render, your heart stops. This isn't a random burst of radiation or a typical thermal signature. This signal shows something that shouldn't exist. It shows a massive, fully formed, incredibly complex structure that is far too old for the timeline of our universe. It is as if you walked into a nursery and found a newborn infant sitting up and solving advanced calculus. This is the signal that has sent the scientific community into an absolute tailspin. It doesn't just challenge our theories. It effectively breaks everything we thought we knew about the beginning of time itself. Stick with me, because we are going to dive into the data, the mystery of the impossibly early galaxies, and why this single discovery might mean the Big Bang never happened the way we were told. To understand why this signal is such a huge deal, we have to talk about the James Webb Space Telescope. For decades, the Hubble Space Telescope was our premier eye in the sky. It gave us breathtaking views of the cosmos, but it had a limit. Because the universe is expanding, the light from the most distant objects gets stretched out as it travels through space. This is a phenomenon called redshift. By the time the light from the very first galaxies reaches us, it has been stretched so much that it is no longer visible to the naked eye. It has moved into the infrared spectrum. Hubble could only see a tiny bit of that infrared. The James Webb Space Telescope, or JWST, was specifically designed to be an infrared powerhouse. It was built to peer back through the literal fog of time to see the first light. When NASA began receiving the first deep field images from JWST, they expected to see small, chaotic, primitive blobs. According to the standard model of cosmology, it takes billions of years for gravity to pull enough gas and dust together to form large, structured galaxies like our Milky Way. In the early universe, just a few 100 million years after the Big Bang, everything should have been small and disorganized. But the signal that came back showed exactly the opposite. JWST found 6 massive galaxies that existed only 500 to 700 million years after the Big Bang. These galaxies aren't just big, they are monsters. Some of them appear to have as many stars as the Milky Way does today. This is the equivalent of looking at a Polaroid of a toddler and seeing a fully grown man with a beard. It simply doesn't fit the biological, or in this case, cosmological timeline. The lead researchers at the University of Colorado and other institutions were so shocked by this signal that they initially thought it was a mistake. They called these objects universe breakers. If these galaxies are as old and as massive as the signal suggests, then our entire understanding of how matter formed after the Big Bang is fundamentally wrong. We thought that dark matter acted as a slow scaffolding, gently pulling gas together over eons. But this signal suggests that the universe was a fast-paced construction site, building skyscraper-sized galaxies in the time it should have been making mud huts. So how is this possible? One theory that is gaining traction and causing a lot of heated debates is that the Big Bang didn't happen exactly 13.8 billion years ago. Some physicists are suggesting that the universe might be much older, perhaps even twice as old. If the universe is actually 26 billion years old, then these mature galaxies would have had plenty of time to grow. But changing the age of the universe isn't like changing the date on a calendar. It ripples through every equation we use in physics. It changes the rate of expansion, the nature of dark energy, and the very composition of space-time. This signal has cracked the foundation of the standard model, and the cracks are widening every day. But there is another, perhaps even more mind-bending possibility. What if the signal isn't just about galaxies? What if we are seeing evidence of primordial black holes? Some scientists argue that the only way to build a galaxy that massive, that quickly, is to have a massive black hole at the center acting like a gravitational vacuum cleaner, sucking in massive amounts of gas at an incredible rate. But where would those black holes come from so early? They would have had to exist asterisk before asterisk the first stars. This leads us to the wild idea that black holes weren't formed from collapsing stars, but were created by the sheer density of the early universe itself. If the signal is showing us these primordial giants, it means the very early universe was a much more violent and high-energy place than the smooth Big Bang model predicts. Now let's look at the cosmic dawn signal discovered by the EDGES experiment. This was a radio signal detected from a time about 180 million years after the Big Bang. This signal was incredibly faint, a specific dip in the radio background caused by the very first hydrogen atoms absorbing starlight. But when scientists measured the temperature of that hydrogen based on the signal, it was twice as cold as it was supposed to be. In physics, if something is colder than the lowest possible theoretical temperature, it means something is sucking heat away from it. The only thing that could interact with normal matter in such a way, without being seen, is dark matter. This signal might be the first direct evidence that dark matter isn't just a heavy, invisible weight, but something that cools the universe through a specific type of interaction. If that's true, we are looking at a new physics that goes beyond anything in our textbooks. But wait, there is more. We have to talk about the axis of evil. No, this isn't a political term. It is a signal in the cosmic microwave background, the afterglow of the Big Bang that appears to align perfectly with the plane of our solar system. According to the principle of isotropy, the universe should look the same in every direction on a large scale. The Big Bang should have exploded outward in a perfectly random, chaotic fashion. But sensors from the Planck satellite and WMAP have confirmed a great alignment in the temperature fluctuations of the sky. It is as if the universe has a preferred direction, a north pole that spans billions of light years. This signal suggests that the universe isn't a random bubble, but might have a specific shape or even a rotation. If the universe is rotating, it implies that it is contained within something else, or that the Big Bang wasn't a central explosion but a much more complex event. These signals from 13 billion light-years away aren't just old news. They are reaching Earth right now, hitting our sensors, and forcing us to question the very nature of reality. Imagine the frustration of the scientific community. We spent decades building the Lambda CDM model, the standard model of the universe, and it worked perfectly to explain everything we could see. But the second we got a better camera, the James Webb, the model started to crumble. It's like believing the world is flat because you can only see to the horizon, and then suddenly climbing a mountain and seeing the curvature of the Earth for the first time. The signal JWST captured is our view from the mountain, and the flat theories of the past are no longer sufficient. So why does this break everything? Because physics relies on a chain of events. If you change the beginning of the chain, the Big Bang and the early formation of matter, you have to change the middle and the end. If galaxies formed differently, then stars form differently. If stars form differently, then the elements that make up our bodies, carbon, oxygen, nitrogen, were synthesized at different rates and in different environments. This means the very atoms in your hand right now have a history that might be billions of years older or more complex than we ever imagined. We are currently living through a cosmological crisis. That isn't my term, that is the actual phrase being used in scientific journals. Let's look into the tired light hypothesis. This is an old idea from the 1920s that is suddenly being resurrected because of these new signals. Fritz Zwicky, a famous astronomer, once suggested that light doesn't get redshifted because the universe is expanding, but because the photons simply lose energy as they travel across vast distances. They get tired. For decades, this idea was laughed at because it didn't fit other observations. But now, as we see these massive galaxies that appear too mature for their age, some physicists have combined the tired light theory with the expansion theory. They found that if you combine both, the math suddenly allows for a universe that is 26 billion years old. This would perfectly explain the JWST signal. The problem? If light gets tired, it breaks the fundamental laws of electromagnetism and relativity as we know them. We are at a point where we have to choose between a broken timeline or broken physics. There is no middle ground. There is also the quasar signal. Quasars are the brightest objects in the universe, powered by supermassive black holes at the centers of galaxies. We've received signals from quasars that existed only 600 million years after the Big Bang, and they are already powered by black holes that are a billion times the mass of the Sun. To grow a black hole that big, it would have to swallow the equivalent of an entire star every few years, non-stop since the beginning of time. This is super Eddington accretion, a rate of growth that should be physically impossible because the radiation from the infalling matter should push the rest of the gas away. The signal from these quasars is basically shouting at us that we don't understand how gravity works at high densities in the early universe. And what about the Lyman alpha forest? This is a pattern in the light signal from distant quasars that shows how much neutral hydrogen was in the space between us and the source. By studying this, we can see the reionization of the universe, the moment when the first stars turned on and burned away the dark fog of hydrogen. The signals we are getting now show that this process happened much earlier and more unevenly than we predicted. It was like a giant cosmic firework display where the entire universe lit up in a chaotic, fast-moving wave. This suggests that the first stars weren't just the tiny, blue suns we imagined, but POP3 stars, monsters that were hundreds of times larger than our sun and lived for only a few million years before exploding. These stars would have been the seeds for the massive galaxies JWST is seeing. But we haven't found a single direct signal from a POP3 star yet. They are the missing link of the cosmos. Think about the sheer distance involved here: 13 billion light-years. Light travels at 186,000 miles per second. In the time it took you to breathe just now, light traveled millions of miles. Now imagine that light traveling for 13 billion years. It has passed through galaxy clusters, been warped by the gravity of black holes, and survived the expansion of space itself. When it finally hits the gold-plated mirrors of the James Webb, it is carrying the ultimate time capsule. And the capsule is telling us that the oldest things in the universe look shockingly similar to the new things. If the early universe looks like the current universe, it challenges the idea of evolutionary cosmology. It suggests that perhaps the universe has always looked this way, or that it goes through cycles of expansion and contraction. The Big Bounce theory. The Big Bounce suggests that our Big Bang wasn't the beginning, but just the most recent expansion phase following the crunch of a previous universe. If that's true, the massive galaxies we are seeing might be holdovers or seeds from the previous cycle. The signal wouldn't be breaking the timeline. It would be showing us a much larger timeline than we ever dared to imagine. This would solve the infant calculus problem. The infant isn't a newborn. It's a reincarnated master. But the Big Bounce requires dark energy to behave in ways that we haven't observed yet. It requires the universe to slow down and eventually move backward. Let's talk about the tension. There is something called the Hubble tension. This is a conflict between two different ways of measuring how fast the universe is expanding. One way is to look at the local universe, nearby stars and supernovae. The other way is to look at the deep universe, the cosmic microwave background signal from 13 billion years ago. These two methods give different results. They don't just differ by a little bit. They are statistically incompatible. This tension is telling us that there is a fundamental piece of the puzzle missing. Maybe it's a new type of particle, a dark radiation that existed in the early universe, or maybe it's that gravity itself changes strength over billions of years. The signal from the deep past is literally tugging against the signal from the present, and the bridge between them, our current laws of physics, is snapping. This brings us to the most controversial part of these new signals. If the universe doesn't fit the Big Bang model, does that mean the Big Bang never happened? Not necessarily. Most scientists agree that the universe was once very hot and very dense. But the inflation theory, the idea that the universe expanded faster than light in its first trillionth of a second, is under heavy fire. The JWST signals show a universe that is much too smooth and structured for the chaotic inflation model. If we lose inflation, we lose our best explanation for why the universe looks the same in every direction. We are back to square one. We are looking at a sky that makes no sense according to our current math. Think about the impact this has on our place in the universe. We've always felt that we are sitting at the end of a long, clear history. We came from stars. Stars came from gas, and gas came from the Big Bang. It's a nice, neat story. But the signal from 13 billion light-years away is telling us that the story is much more mysterious. It's as if we found a missing chapter at the beginning of a book that changes the meaning of the entire plot. We aren't just stardust. We might be the product of a much older, much stranger cosmic process that we haven't even named yet. And what about the water signal? Recently, astronomers detected the signal of water vapor in a galaxy 13.1 billion light-years away. Water is made of hydrogen and oxygen. Hydrogen was created in the Big Bang, but oxygen is only created inside the hearts of dying stars. For there to be enough water vapor to be detected that far back, a generation of stars must have already lived, died, and exploded to seed the galaxy with oxygen. This has to happen in an incredibly short window of time. The signal shows that the cosmic chemistry was happening at breakneck speed. Life, or at least the ingredients for it, could have been possible almost immediately after the universe became transparent. This pushes the search for life back from billions of years to mere hundreds of millions. This leads us to the anthropic principle. Some suggest the universe is fine-tuned for life. If these early galaxies formed so efficiently and seeded the universe with the heavy elements so quickly, it almost seems like the universe was waiting to create planets and life. The signals we are receiving aren't just about cold gas and gravity. They are about the very potential for existence. If the universe broke our expectations by being too good at making galaxies, it opens up a whole new realm of questions about why the constants of physics, the strength of gravity, the charge of an electron, are exactly what they are. NASA and other space agencies are now adjusting their entire future strategies based on these signals. There is a new push for LISA, a space-based gravitational wave observatory. While JWST sees light, LISA will hear the ripples in space-time. These ripples can travel through the dark ages before the first stars. Scientists hope that by listening to the early universe, they can find out what was really happening when those massive galaxies were being built. If gravity waves show that black holes were merging at an insane rate 13 billion years ago, it will confirm that the early universe was a black hole factory. This would provide the engine needed to explain the massive structures JWST found. But for now, we are in a period of creative chaos. Theoretical physicists are coming up with wild ideas every day. Modified Newtonian dynamics, or MOND, dark matter decay, variable speed of light. Everyone is trying to be the next Einstein who finds the simple equation that makes all these broken signals make sense again. The universe breaker galaxies aren't just a problem to be solved. They are a gift. They are the evidence that we are on the verge of a paradigm shift. Every time science breaks, something better and more accurate is built in its place. Imagine being the first person to truly solve this. Imagine finding the reason why the 13-billion-year-old signal looks so modern. It would be a eureka moment on par with the discovery of the heliocentric solar system or the theory of evolution. We are looking at the DNA of the cosmos. But we've just realized we've been reading the code backward. The James Webb Space Telescope has given us the data, but it's up to our collective curiosity to interpret the meaning. What's also interesting is how these signals are affecting the public perception of space. For a long time, we thought we had it all figured out. Space was settled, but now the mystery is back. The public is realizing that the universe is still wild. It's still full of surprises that can make a PhD-level astrophysicist scratch their head in confusion. This is the most exciting time to be interested in space since the Apollo moon landings. We are exploring the deep past with the same intensity that we once explored the moon. Think about the light echoes. Sometimes, light from a distant explosion hits a cloud of gas and echoes toward us. We are receiving echoes from the very dawn of time. These echoes are distorted, stretched, and faded, but they carry the truth. The truth is that the universe is more complex, more ancient, and more structured than our simplest models allowed for. Whether the answer is that the universe is twice as old, or that dark matter is a coolant, or that the Big Bang was just a bounce, the result is the same. Our old world is gone. We are living in a new universe now. Every time JWST points its mirrors at a blank patch of sky, it finds thousands of galaxies. There is no such thing as empty space. Every direction we look, we see a signal of a bustling, energetic, and massive past. The Dark Ages were never really dark. They were just hidden from our old eyes. Now that we can see, we realize the cradle of the universe was a lot more crowded and a lot more mature than we ever suspected. So where do we go from here? The next few years will be a period of intense observation. We need more data points. We need to find even more universe breakers to see if they are the rule or the exception. We need to look for gravitational lensing, where a foreground galaxy cluster acts as a magnifying glass for the deep background. This allows us to see these impossibly early galaxies in even higher resolution. If we see spiral arms and organized disks in galaxies from 13 billion years ago, then the Big Bang model is officially dead. If they are just massive, glowing spheres, then maybe we can save the model with some tweak to how gas cools. The signal from 13 billion light-years away is a reminder that we are small, we are late to the party, and we have so much left to learn. It's a humbling and exhilarating thought. We are the universe observing itself, and the universe just handed us a puzzle that is going to take generations to solve. Every radio wave, every photon, and every gravitational ripple is a piece of that puzzle. We are listening to the heartbeat of the beginning of time, and it sounds nothing like what we expected. This is the beauty of science. We don't hide the broken parts, we lean into them. We celebrate the signals that don't fit because they are the signs of the unknown. And in the unknown is where all true progress is made. NASA didn't just find a signal that breaks everything. They found the doorway to the next level of human understanding. The universe is much, much bigger than our theories, and it isn't afraid to show us how wrong we are. As you look up at the stars tonight, remember that the static dots you see are just the surface. Behind them, in the deep infrared, are the universe breakers, the massive ghosts of a past that shouldn't exist. They are there right now, their light falling on our planet, carrying the secret of how it all truly began. We are just beginning to read the first few words of that secret, and those words are already screaming at us to wake up and rethink everything. Thank you for joining me on this journey across 13 billion years of space and time. It's a lot to process, but that's the fun part. The cosmos doesn't give up its secrets easily, and that's what makes the chase so worth it. Keep your eyes on the stars and your mind open to the impossible, because the data is coming in, and it's telling us that the universe is far stranger than we can ever imagine. Stay curious, stay informed, and never stop asking why. The signal is out there, we just have to keep listening. I'll see you in the next one as we continue to track the signals that are rewriting our history.